Welcome to one of the most advanced aircraft factories on Earth. What you're about to witness is something very few people ever see.
The bauxite ore arrives at the refinery where it undergoes the Bayer process, a chemical transformation that separates pure alumina from the raw earth.
Brosen. Inside the smelter, alumina transforms into pure molten aluminum through electrolysis.
The molten aluminum is cast into enormous ingots, each one weighing as much as a school bus. These solid blocks of
Before a single gram of this aluminum can be used in aircraft construction, it must pass rigorous quality testing.
The solid ingots now face the rolling mills, massive machines that apply over 10,000 tons of pressure to flatten the aluminum into sheets.
Cold rolling brings the aluminum to its final dimensions with surgical precision. These sheets must be perfectly uniform.
Heat treatment transforms ordinary aluminum into aerospace-grade alloy by heating the metal to nearly 500 degrees, then rapidly cooling it in water.
Before assembly, every aluminum sheet undergoes chemical surface treatment. Acid baths strip away oxidation.
After months of refinement, the aerospace-grade aluminum finally arrives at the aircraft factory. But it doesn't arrive alone. Titanium for landing gear.
Accepted materials enter the climate-controlled storage facility where conditions are maintained within fractions of a degree. Composite materials are kept refrigerated to prevent premature curing. The first cuts begin. Water jet cutters firing at 3 times the speed of sound slice through aerospace aluminum with incredible precision.
Trust but verify. That's the rule in aerospace manufacturing. Even though suppliers certify their materials,
Flat panels must become curved skins that wrap around the cylindrical fuselage. Stretch-forming machines apply hundreds.
Weight is the enemy of flight. Chemical milling dissolves unwanted aluminum with surgical precision, creating waffle cylinders. A single fuselage panel may require over 3,000 perfectly positioned holes. Automated drilling machines work to...
Before panels can be assembled, they receive their first protective coating, aerospace primer that will guard against corrosion for the aircraft's entire service life.
After weeks of processing, from bauxite mine to refined aluminum, these components are finally ready for assembly.
Every panel undergoes exhaustive inspection before joining the assembly line. Coordinate measuring machines verify dimensions to thousandths of an inch.
Terminals. The aircraft skeleton begins with fuselage frames, the circular ribs that will support the skin and resist the crush.
Stringers are the spine of the fuselage, long aluminum profiles that run from nose to tail, connecting the circular frames and supporting the outer skin. The passenger cabin floor doesn't simply rest on the fuselage. It's supported by precision-engineered floor beams that span near. Wing ribs give the wing its aerodynamic shape, the carefully calculated curves that generate lift.
The wing spar is the single most critical structural component of the aircraft, the backbone that carries the entire weight of the fuselage during flight.
The landing gear must absorb the tremendous impact of touchdown. Hundreds of tons of force concentrated into seconds.
Modern aircraft increasingly rely on carbon fiber composites, materials stronger than steel at a fraction of the weight. The autoclave transforms soft, layered composite into rigid, structural material, under 6 atmospheres of pressure and heat.
The danger with composites is that defects can hide within the material, invisible from the surface. Ultrasonic
Subassembly brings panels, frames, and stringers together for the first time. These large sections,
Fuselage sections meet in circumferential splices, joints that must carry tremendous loads while maintaining the wings of a jumbo jet hold over 200,000 liters of fuel, contained not in separate tanks, but within the wing structure. The wing box is the heart of the aircraft structure, the point where wing meets fuselage, and where the greatest loads concentrate. The wing skin does more than cover the structure. It carries flight loads, contains fuel, and defines the aerodynamic shape that generates lift.
The tail assembly, or empennage, provides the stability and control authority that makes the aircraft flyable.
The vertical control surfaces are the aircraft's muscles, translating pilot inputs into physical movement through the air. Built from composite skins over honeycomb cores. Hydraulic fluid is the aircraft's lifeblood, pressurized to 3,000 pounds per square inch and flowing through miles of tubing to power every critical system.
The landing gear is the aircraft's connection to Earth, the structure that absorbs the violence of landing and supports the aircraft's full weight on the ground.
A jumbo jet contains over 500 kilometers of electrical wiring, enough to stretch from London to Paris.
Every major system is tested before it reaches the aircraft. Landing gear cycles hundreds of times on test rigs. Hydraulic systems are pressurized and checked for leaks.
Welcome to the final assembly hall, one of the largest buildings ever constructed by human hands.
The fuselage sections meet for the final time. These joints must be perfect, and the cabin will pressurize and depressurize.
The tail cone completes the fuselage envelope, tapering to a point that minimizes aerodynamic drag. Inside, this is the most critical moment in aircraft assembly, the wing-to-body join. Every force that keeps the aircraft aloft passes through this connection.
The nose section gives the aircraft its face, the streamlined profile that passengers see from the terminal.
A wing misaligned by even a fraction of a degree would compromise the aircraft's flying qualities.
The horizontal stabilizer is the aircraft's balancing mechanism, adjusting its angle to trim the aircraft for changing.
The flight control system is the aircraft's nervous system, converting pilot intentions into physical movement.
The vertical stabilizer rises 6 stories above the ground, a massive airfoil that keeps the aircraft pointed straight ahead.
Over 500 kilometers of wiring now fills the aircraft, carrying power to lights, commands to actuators, and data between computers.
The fuel system must manage over 200,000 liters of jet fuel stored in the wings and center section. Pumps.
The engines are the aircraft's heart, converting jet fuel into the thrust that makes flight possible. Each engine contains a...
The engine pylons form the critical link between power plant and airframe. Each pylon transfers
The moment of engine installation transforms the aircraft from a glider into a powered flying machine.
An installed engine is just the beginning. Dozens of connections must be made before it can run. Fuel lines delivered on it.
The cockpit is where human meets machine, the interface through which pilots will command this 400-ton aircraft.
Conditions. The passenger cabin must serve hundreds of travelers for flights lasting over 16 hours.
The landing gear makes the transition between air and ground possible. Main gear assemblies weighing several tons each must absorb touchdown forces.
For the first time, electrical power flows through the aircraft systems. Computers boot and begin their self-tests. Displays illuminate with flight instruments.
At cruising altitude, the temperature outside the aircraft drops to minus 60 degrees Celsius, while passengers expect a comfort.
The passenger cabin takes its final form as interior panels hide the complexity beneath.
Precisions. Overhead bins represent a constant engineering battle. Passengers want more space for carry-on bags, while airlines...
Galleys and lavatories are marvels of compact design. These modules arrive pre-assembled and tested.
Passenger seats seem simple, but represent decades of engineering optimization, balancing comfort, weight.
Modern in-flight entertainment systems rival home theaters, hundreds of movies, thousands of songs, live television, and Below the passenger cabin, cargo holds carry baggage, mail, and freight worth millions. These spaces must be secure against fire.
The cabin must maintain pressure at altitudes where the outside atmosphere is too thin to breathe. Pressurization testing subjects you. In the paint shop, the aircraft receives its identity. Hundreds of liters of specialized aerospace.
Paint serves more than aesthetics. It protects the aircraft from corrosion and reduces drag through its smooth finish.
The details define the aircraft's identity. Airline logos crafted by famous designers take their place on it. Paint must cure fully before the aircraft can face weather and operations. During curing, quality team
Paint can interfere with aircraft systems if not carefully controlled. Sensors masked during painting must be verified operational.
Engine ground transfer satisfied.
Flight controls translate pilot intentions into aircraft movement, then they must respond correctly every time.
Modern aircraft depends.
The fuel system must reliably deliver over 200,000 liters of jet fuel to the engines, while precisely measuring the remaining quantity.
Landing gear must retract reliably after every takeoff and extend reliably for every landing. Ground testing.
Before the aircraft can fly, it must pass a comprehensive inspection, more thorough than any it will see again.
The night before first flight carries a unique tension. Years of design, months of manufacturing. The test crew boards with the weight of responsibility visible on their faces. These pilots have flown first flight engines running. The aircraft moves under its own power for the first time. The taxi to the runway tests steering response, brake feel, and the
first flight morning begins before dawn. The aircraft is towed to the runway as the test crew performs the most thorough walk-around of their careers.
Rotate.
The nose rises and the wheels leave the earth. The landing gear retracts. On the ground, those who built it erupt in celebration. The nose rises and the wheels leave the earth.
Roll response nominal.
Pitch damping within limits.
With the aircraft safely airborne, testing begins immediately. Systems that worked perfectly on the ground must now prove themselves in flight. Pressurization must maintain cabin altitude as outside air thins to nothing.
The captain guides the aircraft down the glide path, across the threshold, through the flare. Wheels touch concrete for the first time since leaving.
The engines fall silent, and the test crew emerges to a hero's welcome. For the workers,
first flight proved the aircraft can fly. The test program proves how well it flies and what limits it can safely.
Passengers expect their aircraft to operate in any weather, so test flights deliberately seek conditions most would avoid.
The manufacturer's tests verify that the aircraft works. Certification tests verify it meets regulatory standards for carrying passengers.
The type certificate represents the regulatory authority's declaration that this aircraft design meets every
airline on faith.
The airline isn't buying on faith. Their inspectors examine every aspect of the aircraft before
While the test aircraft prove the design, customer aircraft are built to individual airline specifications.
The airline's own pilots must approve the aircraft before delivery is complete. They evaluate handling equipment.
The aircraft departs the factory for the last time, bound for its new home at the airline's hub. The airline crew. And so the journey is complete. From bauxite pulled from the earth to aluminum refined into smelters. And so the journey is complete. From the first machine part to the final rivet. From first flight to delivery, all of it led to this moment.